In this video, we look at how Lewis symbols for individual atoms can be used to create Lewis structures of molecules to give us a greater understanding of the bonding that exists in molecular substances. And we're going to start with the simplest molecular substance, the hydrogen molecule or the H2 molecule. And we can represent the formation of the covalent bond in the H2 molecule using Lewis symbols such as these, where the single electron from one of the hydrogen atoms comes together with the single electron from the other hydrogen atom to form the covalent bond. Now remember, a covalent bond involves the sharing of a pair of electrons between two atoms, so that in this case both hydrogen atoms now are surrounded by two electrons, which is a much more stable arrangement compared to the single electron case. A bonding pair of electrons such as this is typically represented using a straight line joining the two atoms. In the slightly more complicated case of the ammonia molecule, NH3, the Lewis structure can be determined by consideration of the Lewis symbols for its constituent elements, where we see that the single electron associated with each of the three hydrogen atoms pairs up with valence electrons surrounding the nitrogen atom to form three covalent bonds. Again, the covalent bonds are best represented using straight lines joining the atoms. In this case, the ammonia molecule is said to have three bonding pairs of electrons and one non-bonding pair of electrons. And non-bonding pairs of electrons are also sometimes called lone pairs of electrons, and they're represented in Lewis structures as a pair of dots adjacent to the atomic symbol. You'll also note that the nitrogen atom has a complete octet of electrons, thus satisfying the octet rule, and each of the hydrogen atoms has a complete duet of electrons, satisfying the stable arrangement of two electrons for hydrogen atoms. Lewis structures for molecules and molecular compounds are drawn according to the following conventions. Each atom is represented by its atomic symbol. Only valence electrons are used to draw Lewis structures. No inner or core electrons are shown on the Lewis diagrams. Bonding pairs of electrons shared between atoms are represented by a straight line joining the atoms, and up to three bonding pairs of electrons can exist between atoms. Non-bonding electrons on atoms are drawn as dots next to the atomic symbol of that atom, and they usually occur in pairs, which are also referred to as lone pairs. Now, as I said a moment ago, up to three bonding pairs of electrons may be shared between atoms. When one pair of electrons is shared between atoms, this represents a single bond, and it's drawn as a single straight line. When two pairs of electrons are shared between atoms, this represents a double bond, and it's drawn as two straight lines. And when three pairs of electrons are shared between atoms, this represents a triple bond and is drawn as three straight lines. Now, to illustrate the differences between each of these, let's consider the Lewis structures for three diatomic molecules, namely elemental fluorine, elemental oxygen, and elemental nitrogen. In the case of two fluorine atoms coming together, each atom has 7 valence electrons, which in the Lewis symbol are arranged as three pairs of dots and one single dot around the atomic symbol. The single electrons from each atom are able to be shared between the two atoms to form a single covalent bond, resulting in a complete octet for both atoms. The single bond is again best represented as a single straight line. In this case, each fluorine atom is said to contain one bonding pair of electrons, which is localized in a region along the internuclear axis, and three non-bonding pairs of electrons located in regions away from the internuclear axis. In the case of oxygen, each oxygen atom has 6 valence electrons arranged as two pairs of dots and two single dots around the atomic symbol. Here, 2 electrons can be shared by each atom, resulting in a double bond, that is, 2 pairs of electrons drawn between the two atomic symbols. And again, these covalent bonds are best represented using straight lines, and in this case 2 lines representing the 2 pairs of electrons that constitute the double bond. By forming the double bond, each oxygen atom has a complete octet of electrons, resulting from 2 bonding pairs of electrons localized in a region along the internuclear axis, and 2 non-bonding pairs of electrons located in regions away from the internuclear axis. In the case of nitrogen, each nitrogen atom has 5 valence electrons arranged as 1 pair of dots and 3 single dots around the atomic symbol. Here, 3 electrons can be shared by each atom, resulting in a triple bond, that is 3 pairs of electrons drawn between the 2 atomic symbols. And again, these covalent bonds are best represented using straight lines, in this case 3 lines representing the 3 pairs of electrons that constitute the triple bond. By forming the triple bond, each nitrogen atom has a complete octet of electrons, resulting from 3 bonding pairs of electrons localized in a region along the internuclear axis, and 1 non-bonding pair of electrons located in a region away from the internuclear axis. The Lewis structures for the diatomic molecules shown so far are fairly straightforward to draw. If, however, we want to consider Lewis structures for polyatomic molecules containing more than 2 atoms, then we need to consider a more systematic approach. The first thing we need to do when drawing Lewis structures is to sum up all of the valence electrons from all of the atoms present. We then write atomic symbols for all the atoms involved to show which atoms are connected. We then complete the octet for all peripheral atoms bonded to the central atom. If there are any leftover electrons, we place them on the central atom, and if there are not enough electrons to give the central atom an octet, we form multiple bonds. Now, as with any set of rules, they're best demonstrated using an example, and we will use those rules to construct a Lewis structure for the polyatomic molecular compound phosphorus trichloride, PCl3. So the first thing we do is we need to sum the valence electrons from all atoms present. And what we're going to use is the Roman numeral group number from the periodic table to determine the number of valence electrons for each atom. So we've got our molecule PCl3, phosphorus trichloride. It has 1 phosphorus atom. Phosphorus is in group 5A of the periodic table and has 5 bonding electrons, or 5 valence electrons. Chlorine is in group 7A of the periodic table, and each chlorine atom has 7 electrons. Now there are 3 chlorine atoms in the PCl3 structure, which represents a total of 21 valence electrons from those 3 chlorine atoms, thus giving us a total of 26 valence electrons in total across the 4 atoms. Now, if we were looking at drawing the Lewis structure for a polyatomic anion, for example the nitrate anion, we would need to add the number of the negative charge to this total of valence electrons. So if you had a 1- polyatomic ion, you would need to add 1 electron to the total when you're summing up all of the valence electrons. If you had a 2- charge, you would need to add 2 electrons. Along a similar vein, for polyatomic cations with a positive charge, for example the ammonium ion, we would need to subtract the number of the positive charge from the total number of valence electrons. So if we had a 1+ charge, we would subtract 1 electron from all of the valence electrons. If we had a +2 charge, we'd subtract 2 electrons, and so on. So at the moment, for our PCl3 molecule, which is not a polyatomic ion, we've got a total of 26 valence electrons available for bonding. Step 2 is we write the atomic symbols for all the atoms involved to show which atoms are connected. And we've got to define a central atom, and the central atom is typically the most electropositive or the least electronegative atom, and in this case phosphorus is more electropositive or less electronegative compared to chlorine, and so we would place phosphorus as the central atom, and we would connect the phosphorus atom to the chlorine atoms using a single line representing a single pair of bonding electrons, in other words, a single bond. Now, if the structure happens to contain double bonds, we'll address this later in Rule 5, but we just start with single bonds to start with. The next thing we do is we complete the octets for all of the peripheral atoms bonded to the central atom. So we're going to complete octets for these 3 chlorine atoms, and we do this by adding 3 pairs of electrons to the atomic symbol of the peripheral atoms, giving each of them a total of 8 electrons. So there's the 3 non-bonding pairs of electrons around chlorine, plus the bonding pair that it's got where it's attached to the phosphorus gives it 8 electrons, completing its octet. We do the same for the second chlorine atom and the same for the third chlorine atom. Now, the exception here is if hydrogen is one of the peripheral atoms, because we know hydrogen can only accommodate 2 electrons in its valence shell, and those 2 electrons will come from the straight line bond that's already been drawn. Remember, for the hydrogen atom, we think in terms of a duet rather than an octet. So at the moment, we've used 24 of the available 26 electrons. We've got 3 sets of 8 electrons around all those chlorine atoms, representing 24 of the available 26 electrons. What we do now is place any leftover electrons on the central atom, and we have 2 leftover electrons, and we do this even if it gives the central atom more than an octet, and we'll discuss exceptions to the octet rule later on. But there are the 2 leftover electrons, and we place them on the central phosphorus atom. Rule number 5, if there are not enough electrons to give the central atom an octet, we need to form multiple bonds. Now, we do this by using 1 or more pairs of the non-bonding electrons from the peripheral atoms. But in this case, we can see that the central phosphorus atom does have 8 electrons surrounding it, 3 bonding pairs of electrons plus 1 non-bonding pair of electrons, so a total of 8 electrons. We can also see that each of the chlorine atoms has 8 electrons surrounding it as well, so everything there satisfying the octet rule. So rule number 5 is not relevant here. We're not going to form double bonds, and the central atom has 8 electrons, as do all of the peripheral atoms. So that's the structure there, the Lewis structure for the molecule phosphorus trichloride, PCl3.